Hello, my name is Andrius Vaicenavičius, and I'm a PhD student at the University of Oxford. And it is my pleasure today to present at the Explainable Logic-Based Knowledge Representation Workshop my joint work with Dr. Ismail, Ilkan, Ceylan, Professor Thomas Lukasiewicz, and Dr. Enrico Malizia. This work is on explanations for query answers under existential rules. So first of all, I would like to start by reviewing some of the existing work. So earliest work on abductive reasoning, that is explaining the observed consequences, used propositional logic to model the situation. So propositional theory, was used to model the application domain. For example, in this example, these propositional sentences express that rich mixture and lean mixture in our engine cannot occur together. Rich mixture leads to high fuel consumption, lean mixture to overheating, and low oil to overheating too. Then a set of atomic formulas describe manifestations, that is, observations that we want to explain. So in this case, we have observed high fuel consumption and overheating. And the third component is a set of hypotheses. In this case, rich mixture, lean mixture, and low oil. This is the set of hypotheses that part of it forms an explanation. So what is an explanation? Explanation is a subset of these hypotheses, which is together with a theory is consistent and logically entails the observed manifestations. Okay? So in our context, we want to explain high fuel consumption and overheating, and given the theory. As it currently stands, note that theory together with a set of hypotheses is not consistent because rich mixture and lean mixture cannot occur together. Okay? So in this situation, for example, rich mixture together with low oil is an explanation for the manifestations. Later in description logics community, axiom pinpointing came about. That is, just given ontology, T-box, that expresses common sense knowledge, we aim to explain ontological consequences. That is, why particular T-box entails some particular axiom. And in this situation, we are looking for a minimal subset of this T-box that still supports the entailment of that axiom. Okay, so this came about in 2000, and then later complexity was analyzed of the problems related to axiom pinpointing. And our work in many ways was inspired by this second work and complexity analysis provided there. And to illustrate how axiom pinpointing works, suppose we have a number of axioms. We are using description logics for this example. So we have a number of axioms, and we see that that in this ontology, concept A4 is not satisfiable, or that this axiom A4 implies bottom is entailed. Okay, so we can see that, for example, if axiom 1, axiom 3, and axiom 4 holds, then we have that both C and not C has to be true, which implies our axiom that A4 is not satisfiable, right? So in this context, the two explanations, also known as justifications, would be axiom 1, axiom 2, and axiom 4. Okay, because in the first case, for all S B and exist as not B are not compatible. And the second one, as we've seen, axiom 1, axiom 3, and axiom 4. Now we move on to our object of study, that is explaining query entailment. That is, why a particular query is entailed by a given knowledge base. The earliest works in this domain concentrated on description logics and providing proof-based explanations. That is, a series of query rewritings. But these query rewritings were based on the concept constructs, and they would work just for restricted description logics. Later there was some work also explaining entailment and inconsistency tolerant semantics. And this work is a bit closer to the flavor of our work. That is, explanations are provided as subsets of the data, or the A box in the description logics context. Now we introduce what we mean by an explanation and give some preliminaries. So first of all, I'd like to take a step back and say what we mean by ontology-mediated query. So suppose we have some data, as a database, and we want to find out something. So we pose a query. But there might be some knowledge which is not captured in the data, right? For example, data can come from different sources. Or we just have some extra knowledge about it, how different facts relate to each other. In that case, we mediate this query via ontology, or in the context of data log plus minus, we call it program. Okay, so in that case, we say then that database entails this ontology mediated query, that is a query together with the program ontology. If and only if for all models of this knowledge base, data together with ontology, we have that the query holds. Okay? And now we introduce what we mean by a minimal explanation. So a minimal explanation for the ontology mediated query in some database is a subset of that database, E, which satisfies the following. First of all, it entails this ontology mediated query, and second of all, is subset minimal. That is, no proper subset of it entails this ontology mediated query. Okay? We illustrate this notion on an example. So we take an example from protein design. So suppose we have 6 proteins, and each protein belongs to one of the 3 complexes, C1, C2, or C3. Okay? And we are seeking a protein cover. That is, we're seeking some subset of proteins that covers all these complexes. Okay? So we can model this as follows. In the database, we have a fact for each protein. In the program ontology, we capture what proteins cover what complexes, right? So for example, P1, protein 1, covers complex green, C1, and red, C3. And we have for each protein a rule. And finally, the query tells us that all complexes are covered. That's what we observed. Okay? And in this situation, a minimal explanation for this query in this database is a subset of proteins that gives a minimal subset of proteins that covers all these complexes, right? So for example, P3 and P5 is a protein cover because it covers complex C1, C2, C3, and is minimal. If we remove either P3 or P5, then we don't cover all the complexes anymore. Not all minimal explanations have to be of the same size. For example, in this case, P2, P4, P6 is a minimal cover, a minimal explanation, because none of these proteins can be removed, and they cover all of the complexes. On the other hand, of course, not all subsets are minimal explanations. For example, this P2, P4, P5, although it covers all the complexes, is not minimal. And some subsets don't cover all the complexes, and that's why they're not protein covers. Okay? So now we introduce problems that we study in this work. The most fundamental problem that we study is min-ex. This is the problem of recognizing a minimal explanation. And this problem is a decision version of the problem of constructing a minimal explanation. Okay? So suppose we have a database and ontology-mediated query, such that database entails this ontology-mediated query, and a subset of a database, E. And we are asking, is this subset E a minimal explanation for this ontology-mediated query? Okay? So on our example, for example, P2, P4, P6, as we've seen, is a minimal explanation. That's why we accept it. Or P1, P5, because still they cover, while some subsets are rejected because they are not minimal explanations. The other fundamental problem is all minics, the problem of recognizing a set of all minimal explanations. And this is a decision version of a problem of constructing the set of all minimal explanations. So given a set of subsets of the database, we are asking, is the set of subsets exactly the set of all minimal explanations for the given ontology-mediated query? Okay? So on our example, we have 7 minimal explanations, that is 7 protein covers. Then we study some more problems, and this problem in particular, min_rel, concerns with the role of a particular fact in explaining the entailment. That is, given a distinguished fact in the database, we are asking, is there a minimal explanation that contains that fact? Okay? So for example, protein 4 on our example. Yes, indeed, it is relevant for explaining because there is a cover that contains it. Another problem, counterpart of the previous one, is asking, given some subsets of facts that we want to avoid, we forbid, right? Is there a minimal explanation that avoids all of these forbidden sets of facts? Okay? And on our example, suppose we forbid these subsets, right? We don't want protein 1 to occur in the minimal explanation. We don't want P3 and P5 to occur together. And we don't want P2, P4, P6 to occur together. Maybe we know that they're incompatible. In that situation, we have that there is a minimal explanation that does not contain any of these forbidden subsets, that is P3, P4. Okay? And then we study also a problem, small minics. This is a problem asking, is there a minimal explanation of the size smaller than some given threshold number? That is, given a number, we're asking, is there a minimal explanation which is smaller than this number? Okay? So, in this situation, we have that there is a minimal explanation, of course, of size 3 and of size 2. So we know that there is both an explanation smaller than, there's an explanation smaller than any number greater or equal than 2. Okay, but there is no explanation of size 1. Now introduce existential rules. This is a first order logic fragment that we use to express ontology, express our common sense knowledge. That is, they take the following form. That on the left hand side of this implication, we call it the body and universal quantification. And the right hand side is existentially quantified and called the head. Okay? And both of them are conjunctions of atoms. Generally, not only first order logic is undecidable, but even existential rules without any restrictions are undecidable. That's why we look into restrictions of existential rules. And the ones that we look into in the rest of this talk is linear, when the body has a single atom, guarded, some body atom contains all body variables, acyclic, predicate graph, that is acyclic, and there are no existentially quantified variables. So our object of study is complexity analysis, is understanding how difficult each of these problems that we've considered is. Right, so all of our results depend on the complexity of query answering. That is the problem of just asking, does this database entail this ontology-mediated query, right? And in our context, we have this complexity. We study a number of complexity measures. That is, which part comes as an input. So for example, in data complexity, only database is part of the input. The ontology-mediated query is fixed. In FP combined complexity, database and the program comes as an input. The query is fixed. BA combined complexity is bounded arity. We know that arity of the predicates is fixed, but both database, query, and the program is part of the input. And in combined complexity, database, query, and the program all come as an input, right? And now we look into the complexity of the first problem, is minics. We generally see that the complexity increases, which is not a big surprise because we in addition to checking entailment, we need to check also minimality. And we concentrate on DP result, that is in the linear fragment of existential rules in FP combined complexity, where query is fixed, just database, and the program comes as an input. Okay, so DP just is a class of problems that are decidable with a single NP call and a single co-NP call. Okay, so we just show for Isminix in this case just membership result, because hardness result is slightly too complicated to present here. So we can decide Isminix by checking that this subset of the database E entails the ontology-mediated query, and that no proper subset of E entails via this ontology-mediated query, right? That is minimality. So we can check entailment in NP, because checking entailment in linear fragment in FP combined complexity is in NP. And now we need to check that no proper subset of E entails this query. It is equivalent to checking that removing any element from E breaks the entailment, because non-entailment is preserved by removing elements. So this takes a linear number of non-entailment checks. And because entailment is NP, non-entailment is in co-NP. So these tests can be combined as a single co-NP test. Okay, so we need an NP and co-NP test, which is DP. In the paper, we also provide DP hardness result, and we encourage the reader to look into that, why Isminix can express these other DP complete problems. Another fundamental problem is all Minix, the problem of recognizing the set of all minimal explanations. And we show the membership in the guarded fragment of existential rules in the data complexity. So we show that in this case all Minix is in co-NP. So to decide all Minix, we need to check that a given set of subsets of the database, each subset entails the query, okay, and that every set in the set of subsets is minimal, and that there is no Minix outside of this set. Okay, to check entailment of each subset in this set, we need a linear number of P checks, because in data complexity, in the guarded fragment, each check is P. So we need a single polynomial time check. And then we need to check that every set is minimal, and there is no Minix outside of our set of subsets. But we notice that this is equivalent to checking that there is no subset E dashed of the database that does not contain any subset in our set and entails the ontology-mediated query. Okay, so to see, E dashed might be one of the two, given our database and our set of subsets. E dashed is either contained in one of our subsets, but because it cannot contain any of our subsets, or contains some elements outside, right? So it covers the two cases. If such E dash doesn't exist, it covers both minimality, and then it covers that there is no Minix outside, because there is no subset outside that entails the ontology-mediated query. We can check existence of such E dash in NP, and we want to check that such E dash does not exist. That's why this check is in co-NP. And P and co-NP tests can be combined as a single co-NP test. Similarly, we have a corresponding hardness result in the paper, but we don't present it in this discussion because it's rather complicated. We present a simpler proof which covers some of the ideas. Now we look into Minix-REL, the problem of deciding whether there is a minimal explanation that contains a distinguished fact. That is, whether this distinguished fact is relevant for explaining the entailment of the ontology-mediated query. We concentrate on linear fragment of existential rules in FP combined complexity, and we show that in that case Minix-REL is sigma P2 complete. And sigma P2 class is the class of problems decidable by NP machine calling an NP oracle. So first of all, we show membership. We can check that this distinguished fact psi is contained in some minimal explanation by first of all guessing a subset containing this fact, and this can be done in NP, and then checking whether this subset is indeed a min-x. That is, we use an oracle for is min-x, and we know that it is in DP. And NP, calling DP oracle, which is sigma P2. Now hardness. For hardness, we reduce the following sigma P2 complete problem, a variant of satisfiability problem. That is given at 3CNF formula with two disjoint sets of variables. We are asking, is exist x for all y not phi xy valid, right? So first of all existential and then universal quantification, and not phi. And now, how do we express this problem in our framework? So first of all, for each variable in x, we add two facts, val xi0 and val xi1, to capture assignment to that variable. Then we want to ensure consistency when the same variable appears as a literal, either negated or as a positive. So we use simulate to express that, oh, this variable here appears as the same, as the same literal and opposite literal. Then we have clause sat, fact that captures satisfying assignments to literals. That is that we have 7 of these facts where at least one literal has to be positive, right? And then we have extra one fact which is used in construction to bypass satisfiability check. This actually will be our distinguished fact. We will see how it works. And the program is empty, so this proof actually works not only for linear but actually any fragment that we are considering in FP combined complexity. So the query is the place where we capture both the structure of a formula and the satisfiability of this formula. So it is a conjunction of the following components. So first of all, we ask for all the structural facts that are in the database. That is, all the facts apart from this clause 222. That will be our distinguished fact, is required to be in every minimal explanation. Then the query requires at each variable to be assigned some value. Ti is either 0 or 1. And then we have this assignment is copied to the corresponding literals. That is, it gives assignment to the literals. And then we have a part consist, which is slightly too complicated to present here, which ensures that all literals are consistent. That is, assignment is consistent. And then finally, we just ask that this formula is satisfied. So interestingly, how does this work? So we pick a distinguished fact clause set 222. We have that database without this clause set 222 entails the ontology mediated query if and only if actually this formula negated phi for all x exist y phi xy is valid. So we can remove this distinguished fact only if our formula is not valid. That's why we have that a min-x contains clause set, our distinguished fact, if and only if our phi is valid. So to wrap things up, so we, of course, we provided complexity analysis for min-x rel, small min-x, which we introduced in the beginning. Also, we considered extra one problem, large min-x, which is the problem asking, is there a minimal explanation that is of size greater than some given number n, okay? And then we considered more existential fragments like sticky, guarded full, and weak versions of considered fragments like weak, sticky, and so on. And then we provided, as we've seen, results for data, FP combined, BA combined, and combined complexities. In each of the tables, for each result, we provided both membership and hardness results. So thank you very much for listening, and please let me know if you have any questions. Thank you.